Okay, welcome back. This is now 2.3 in our discrete math book. We want to look now at arguments again. So you'll have a list of statements and followed by a conclusion. But now with, in the context that of our statements, our variables and symbols and all that stuff. And then we're going to be able to see like standard argument forms, just like we had equivalent statements before. We'll kind of try to generalize arguments into particular forms, I guess. Okay, so without further ado, valid and invalid arguments. And I don't know. So later in math, things get so complicated, and you know, I mean, books in math later they just turn into like proof after proof after proof after proof, and there's this kind of like they have to write it in English, so it has to be a paragraph, and it has to all be perfectly valid and logical, and it almost confuses what you're arguing. Okay. So when I read math now, I translate all of the English into kind of logic and symbols and all that stuff. And it becomes easier, in my opinion, in order to kind of hold on to the facts of the argument. Okay, so that's how I use what we're going to be doing here in this section and everyday work. And, you know, it's not work, it's me just sitting around studying math because I teach math, right? But I don't know. If you ever listen to an argument or if you have to read one, like I said, it can be confusing in English. But if you do this translation into logic, in my opinion, it becomes a lot easier to deal with, a lot easier to stomach. And okay, so without further ado, again, 2.3, we have argument forms. And let's take a look at, and hopefully this so let's take a look at, these stupid pages are all out of order. They give us an argument at the bottom of page 68. So it's kind of an example here. So the first statement, if Zeus is human, then Zeus is mortal. Okay. The second statement, Zeus is not mortal. And then the conclusion, Zeus is not human. Okay, we can completely get rid of all the English and just put it in a symbol form using what we've done in the previous section on statement forms. So if Zeus is human, let's say Zeus is human is P. Let's say Q is the statement Zeus is mortal. Sorry about my spelling and my handwriting, it's just terrible. Right. Okay, I think we'll be able to handle it now, right? So if Zeus is human, then Zeus is mortal. So if Zeus is human, then Zeus is mortal, Q. So that's the first statement. And then the second statement, Zeus is not mortal. Okay, so Zeus is mortal is Q, so Zeus is not mortal is not Q. And then finally, the conclusion is going to be, and we could draw like a line like you're doing addition or something. The conclusion, therefore, Zeus is not human, so that's just not P. And whenever you see this kind of argument, we can actually put a name on it. This is going to be, let's see if I can even remember what it was. modus tollens. Okay, so there's going to be all these argument forms that we need to have kind of mastered. I'm going to list those forms here in a second. But let me just introduce the valid argument forms. So this is going to be one of those forms, but let's take a look at them. Okay. Okay. So the first valid argument form, so part A, valid argument forms. In order to see it's valid, all of the okay, so let's just take an example of an argument, right? So I think the argument we just looked at, if P then Q, not Q, therefore not P, right? And we're going to call that modus tollens, right? So write that down. That's modus tollens. We're going to see how to spell it. Tollens. Just looking through my notes. It doesn't seem like I did an example of modus tollens. Oh, okay, well there it is. So I want to make sure this is a valid form, and you're going to use truth tables to kind of establish that, like you did with equivalent statements before. Okay, so how does this work? You're going to do your P and your Q, and then we need our statements. So if P, then Q. Another statement, not Q, and then the conclusion, not P. So we're going to fill out this chart. So true, true, false, false, true, false, true, false. If P, then Q, that's true, false, true, true. Not Q is false, true, false, true. And then not P will be false, false, true, true. Okay, so to figure out if it's a valid form, you look for where the premises are true. So if both premises, in this case, there's only two, so if both are true, it must follow that the conclusion is true. Okay, so you'll find rows where they're both true, so not this one, no, no, okay, right here. And then you look at the conclusion, and the conclusion has to be true for this to be a valid argument. Okay, so this modus tollens is a valid argument. Let's look at one that's not a valid argument. Okay. So in the book, let me find what number it is. I believe it's number 6. Okay. They start with an if then, if P then Q, and then if Q then P, and then the conclusion, either P or Q. Okay. Okay, so determine if that is a valid argument. So we go to our truth table with our P, Q, and then we need a column for the statements, if P then Q, and then we need a column for if Q then P, and then we need a column for the conclusion, P or Q. Okay, so go through and populate true, true, false, false, true, false, true, false. So this will be true, false, true, true. This will be true, true, false, true. And then P or Q, we have to go to these two columns. If either one is true, then this is true. So true, 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 and then false. And then we need to go through and circle the rows where the premises are true, and then look at the conclusion. So this one works. Sadly, this one does not work. So therefore, it's not a valid argument. Okay. So that second row indicates it's not valid. Okay, let's look now at modus, the two main argument forms, modus ponens and modus tollens. Okay. MP and MT for short. First, modus ponens. And basically, if P then Q, and then you know P is true, it forces Q to be true. Okay, so therefore Q will be true. And we can verify, its validity with truth table. Let's not bother. Modus tollens then, MT, the one we just looked at. So if P then Q, not Q, is true. So if this is false, this better be false as well. You kind of have to think of it like that. So therefore not P. And that's your modus tollens. Okay? So for example, if I'm on vacation, then I am happy, is our first statement. If I am on vacation, then I am happy. Okay. The next statement, I am on vacation. So therefore, your conclusion using modus ponens is I must be happy. Okay. So the form here, if I'm on vacation, say that's P, I am happy, let's say that's Q. Okay. You're given that you're on vacation, you're given P, and then you must be able to conclude, well, if P is true, Q must be true. I must be happy. Another example, maybe this is one from the book, number 3. If logic is easy, then I am a monkey's uncle. I am not a monkey's uncle. Therefore, blank. Okay, so what is the form here? This is first, if logic is easy, then so let's say P, logic is easy, then Q, I'm a monkey's uncle. So that's the first statement. The second statement, I am not a monkey's uncle, so they're basically saying not Q. So from modus tollens, then I could say my conclusion must be not P. Okay, so P was being logic was easy, so therefore logic is not easy. Okay. So you're just identifying the form and kind of doing substitutions. Okay. The next part is on fallacies. So this is the kind of thing where you accidentally say, if I hit the ball out of the park, I got a home run. And you accidentally say, well, if I got a home run, I must have hit the ball out of the park. It's those converse and inverse errors in particular that we're looking at. So section 3, fallacies. Okay, so again, recall it is not the case that if you have P then Q, that is not equivalent to its inverse, right? So not P, if not P, then not Q. Okay? And we can go through and show that this won't work. And basically, what the argument usually looks like in that case is something like this. If you have if P then Q, and then your next statement is not P, you may accidentally conclude not Q, right? That would be the inverse error. We also have the converse error. Just very quickly, let me put that then. If P then Q, and then you say Q, and the converse error would be thinking, well, if I hit the ball, if I got a home run, I must have hit the ball out of the park, right? So then you conclude P, and that's also a fallacy, right? So this is the converse error. In particular, you can take a look at the truth table on these guys and show, this isn't going to work. So in particular, if we have our P, our Q, and then our statements here. So statement 1, if P then Q. Statement 2, not P. And then we want to, we're supposing that not Q will follow. Okay, let's go ahead and fill out the chart. We have true, true, false, false. And then we have true, false, true, false. And then we have true, false, true, true. And then we have false, false, true, true. Then we have false, true, false, true. Then circle the rows that have all trues. So true, true. Oh, and that's the problem right there. This one works, but then this one doesn't work. So it's not a valid argument form. Okay, other common argument forms that I hope eventually you have memorized. I think this is section 4 in my notes. The generalization. So basically, if you're given a statement, you can use a disjunction to make it bigger. So maybe the statement is, I'm alive. And then you could basically attach anything you want to that. I'm alive, or I'm living on Mars, and it's still going to be true, right? So generalization P is true, and then you can conclude P or Q. Okay, and you do that thing. So you're expanding, you're making it bigger. And in the book, then they note also, if you're given Q, then it's a bit silly. You could say Q or P, right? That's why there's part A, part B. Okay, so that's the first one. Specialization, you're kind of making it smaller. So if you know that I'm over 45 and I'm alive, you can say, well, in particular, I know I'm over 45. Okay, so specialization, if you have an and statement, you can make it smaller. Okay, you could say, well, if I have P and Q, I can say P. And likewise, if you have P and Q, you can also say Q. All right, conjunction. So if somebody says one statement and then gives you another statement, you can put them together with a conjunction, right? So if somebody says, somebody gives you P and then somebody comes along and gives you Q, you can conclude P and Q. Okay? This is true, and then they give you this is true. Well, this is going to be true because both of them are true. Elimination. So if you have P or Q, and then somebody tells you that Q is not true, for this thing to be true, P has to be true. So you conclude, therefore, P. And then likewise, if you have P or Q, and then somebody tells you P is not true, it must be the case that Q is true. Okay, transitivity. kind of is what you think it is. Activity. So if this is a kind of a, no, I'm not going to give you an example. You can think up your own. If P then Q, and then you have if Q then say R, you can conclude that P will imply R. Okay. So that's transitivity, contradiction. If you're given not P implies a contradiction, so you can conclude that it must be the case that P is true. Okay. And you'll see that happen in proofs a lot. They'll presume that it's not true. It leads to a contradiction, so therefore the problem with your argument is that you assume P was not true. It must be true then. Okay. Contradiction, proof by division in the cases. And now these kind of arguments, these valid arguments, are getting a little more obscure. P or Q, P then R, Q then R. You can conclude R in that case. Okay, so basically you have this statement is true, so you know either P or Q is true. So if P is true in this statement, then R has to be true. Or if Q is true in this statement, that'll imply R is true. In either case, you have that R is true. One more for fun, which may not be in the book, the constructive dilemma. And then we're just going to do some arguments or proofs. Constructive dilemma, if P then R, if Q then S, but I think this is the same, P or Q imply the final conclusion is R or S must be true. So very similar to the last one we looked at. Okay, I would expect you to have most of these memorized, except maybe the constructive dilemma and the proof by division in the cases. Well, no, even that one. This is probably the only one I wouldn't expect to have memorized is this one, and I don't think this one's in the book. Anyways, 37. Let's take a look at what is going on there. Okay, so 37 on page 78. Let me take a quick look at that. In the back of an old cupboard, you discover a note signed by a pirate famous for his bizarre sense of humor and love of logic puzzles. In the note, he wrote that he had hidden a treasure somewhere on the property. He listed 5 true statements below and challenged the reader to use them to figure out the location of the treasure. Okay, so what I'm going to do here is kind of identify the statements inside of each of these statements and give them symbols, and then construct some compound statements and then play around with them to kind of figure out where the treasure is hidden. Okay. Okay. So I've had time to look at it, and I noted I want the following statement variables. So first H, I'll say, is the house next to the lake. I'll say K is the treasure in the kitchen. The treasure is in the kitchen. E, we'll say the tree is the elm tree. F, the treasure is under the flagpole. O, the tree is the oak tree. And then G, the treasure is in the garage. Okay, so I'm going to sort of get rid of the words in this puzzle, and that'll make things easier for me to make a conclusion about where the treasure is. Okay, okay, so I'm going to go back to the question at hand and start sort of figuring things out. So if this house is next to the lake, then the treasure is not in the kitchen. So my first statement, if the house is next to the lake, so that's H, the house is next to the lake, then the treasure is not in the kitchen. Okay, so the treasure is in the kitchen is K, not in the kitchen means not K. Okay, the second statement says if the tree is in the front, if the tree in the front yard is an elm, so E, if the tree is an elm, then the treasure is in the kitchen. So then K. All right. Statement 3, the house is next to a lake. Okay, so the house is next to a lake, that's H. Statement 4, the tree is in the front yard. The tree in the front yard is an elm. Okay, E. Or is an elm. Or the treasure is buried under the flagpole. So that was F. E or F. The last statement, E, if the tree in the backyard is an oak, so that was O, then the treasure is in the garage. Then the treasure is in the garage. That would have been G. I need to figure out where the heck the treasure is, and I'm going to use the argument forms in order to kind of move towards that result. So I need to conclude K, or I need to conclude F. So the treasure is in the kitchen, or the treasure is under the flagpole, or the treasure is in the garage. I need to get to one of those places using the argument rules. Okay. Okay, so the first argument rule I see, and the most common argument rule is modus ponens, right? So 6, this statement and this statement means not K. And you have to kind of tell your reader how you got to that conclusion, right? So this is from statement 1 and statement 3, and it's modus ponens. And you put it in parentheses or something. Okay. 7. Not K plus this statement. That's a modus tollens case, right? So if K is not true, then E can't be true. So we used statements 2 and statement 6, and it's modus tollens. Okay. I can now use the elimination rule, right, on using this and this to get F. So 8, F must be true because E is not true. So I have 4 and 7, and that's elimination. Okay. And is that the answer? Yeah, the treasure is under the flagpole. Okay. Okay, so what you're kind of seeing here is the seeds of these desires from the first part of the 20th century to kind of automatize all thoughts in mathematics. So in mathematics, you'll have axioms. An axiom from geometry, like alternating interior angles, or the alternating angles of a transversal or equal, or something like that. Now, you would have those things as kind of your your prime statements, and then you would have a set of statements, and then you may have statements based on those statements, compound statements, and then you can group them together and work kind of with these argument forms in order to create new statements. And the hope was that you could kind of prove or show everything about mathematics in this way. If you just know some basic axioms, you wouldn't really need to sit around and worry about proving new theorems or anything. You just put it into a computer, and the computer would prove every theorem you ever needed. Right? So that's kind of the seeds of that thought. It turns out that it's not always going to work that way. You can't necessarily program a computer to do that kind of stuff. You have to take like to study Turing machines and Gödel's theorem and I believe Pi Church is in there, Whitehead and Russell, these guys from the beginning of the 20th century. Computational theory, or what was it, recursive function theory with, I don't know, you have to study theory. It's all kinds of, seems like it's computer, kind of theoretical computation type stuff. Anyways, all very interesting, and I'll try to get you even closer to that idea that you could use these kind of arguments in order to prove everything you need in mathematics, which I'm saying is not necessarily going to be the case. Let's look at 41. Okay. So they're going to give you a set of premises, and then you need to use, like we just did in the previous problem, our valid arguments in order to make a conclusion. Okay, so we have not P or Q implies R. S or not Q. They letter them. I like to number my statements. So 1, 2, 3, not T. 4, if P, then T. 5, not P, and R implies not S. And then 6, therefore, well, what we want to prove, I usually like to write it like this. I want to prove not Q. Okay? So these are my premises, and I want to end up here at not Q. Okay? Okay, and you use those valid argument forms. So in the beginning, you probably want to have that page open in your ebook, or if you got the book, just do a snippet and then have it there sitting on your computer so you can look at it, so you know the names. Well, hopefully you get it memorized. Anyways, let's take a look. So I need to get to not Q. And what can I do, right? So this looks like modus ponens and modus tollens are usually the lowest hanging fruits. So here's a modus tollens. So I conclude part 6 that not P is true, and that's from 3 and 4 and modus tollens. Okay. Then I can do a generalization. Well, no, I can't do a generalization. I need an or. Let's see what else I can do. So I got not P. Oh yeah, I can do a generalization to get this statement. So I'll say not P or Q. So that's just generalizing 6. Sorry. Okay. And then you could do a modus ponens on 1. Okay, so you have this part. That implies that R will be true. Okay, so that's from 1 and 7, and that's a modus ponens. So this plus this gives me R. And then now we can go and do a conjunction with not P and R in order to get this. And then we'll have a modus ponens to get not S. Okay, so we'll have not P and R. And that's going to be from 6 and 8. And that's a conjunction. Sorry. Okay? And then I could use 9 and 5 with the modus ponens to get not s. Okay? And then I could do an elimination on 2, because I have not s. That must imply that not q is true. So that was 10 and 2 with elimination. Sorry, went off the page there. And that's what we wanted, right? That's what we wanted to prove. So we got it there. Okay, so again, how does this relate then to math in general? I just want to give you a taste of that. So I want to prove that if you have A greater than B and B greater than C, that implies A is greater than C. Okay, so it's a simple thing, right? But we want to prove it using logic and maybe given some premises about math, about these math statements. So first off, and I'm going to write it in kind of my symbolic form, like I would in, you know, if I was taking a shorthand notes. So the first premise is that if x is in the real numbers, such that we're dealing with the positive reals, okay? So I'm not including 0 in this case. And if y is in the positive real numbers, so this r with the line over there means the real numbers, like the counting numbers, the fractions, the negative fractions, irrational numbers like pi. Those are almost on there, right? But we only want the positive ones, so we throw out the negative guys. It turns out 0 is neither positive or negative, so usually if they want 0 in this book, I believe they put a little 0 down here, okay? But I think in this book it's just positive with a plus sign up and the sort of exponent place. Okay, so if x is in the positive reals and y is in the positive reals, then you could conclude that x plus y is in the positive reals. Okay, and that makes sense. Like if you took 3 plus 7, that's also a positive real number. Okay, so that's our first premise. Our second premise is what this thing really means, this x greater than y. What does that mean? If you have x greater than y, that's equivalent, or if and only if, you have the statement x minus y in the positive real numbers. Okay? So for example, if you think 7 is greater than 2, which it is, and those are both numbers in the positive reals, then that's equivalent to saying that 7 minus 2 is also, and I should make this positive real. Okay? And we note 7 minus 2 is 5, which is a positive real number. Okay, so it's just a way of defining this order relation. Okay, now we want to say specifically A is in the real numbers, the positive reals. Let's say B is also in the positive reals, and that C is in the positive reals. Okay. We're going to start with this side and conclude that this is true. Right? So they're going to give you that A is greater than B, and they're going to give you that B is greater than C. Okay? And we want to end up proving that A is greater than C. Okay, so first off, I'm going to take this statement and use the if and only if part to do kind of a rewrite of this. Okay, A greater than B is the same as saying A minus B is an element of the real numbers. Okay, so that follows from statement 4, statement 3, and then our if and only if statement 2. Okay, then likewise, I could say B minus C is in the positive reals. And that'll follow from 5, 3, 2. Then 8, I can use basic rules of arithmetic to add these two together. And what does that equal? So A minus B plus B minus C equals what? Well, that equals, well, one thing for certain, if this is in the positive reals and this is in the positive reals, then A plus B minus C, if you allow me to, that must be in the positive reals because of this fact. Right? So A minus B plus B minus C is in the positive reals. And then I'll use the algebra, the arithmetic. A minus B plus B minus C is equal to A minus C. And so that must be in the real numbers, the positive reals. Okay, so 8 follows from 6, 7, and 1. 9 follows from basic arithmetic, 8 and arithmetic. And then once you get this statement, you can kind of do a substitution, right? It's the same as this statement, but with A and C instead of X and Y. So if you have this statement, it's equivalent to saying from fact 2 that A must be greater than C. Okay, so that's from 9 and 2, okay, which is what we were trying to prove. Okay, so my point is, if nothing else, you can work from basic axioms, basic facts that we kind of know, and pretty much prove any theorem that you want to. And that's kind of what I was saying with the computer. It would be nice if we could program a computer to do that, you know. It works, you have some basic facts, some basic ideas, and they work as kind of a generator. They kind of work as your, I don't know, XY coordinate system for populating the entire plane with all kinds of weird shaped objects, except now instead of having graphs and lines, you have kind of theorems that are being populated from a smaller set of points in the plane. Instead of points in the plane, now you have axioms. Okay? So it's an incredible thing. You can take thought and translate it into kind of, I don't know, algebra and math. It's just, it blows my mind. And then you hand it to a computer, and the computer does all the thoughts for you. There's nobody making stupid mistakes. There's nobody arguing this. Maybe the implementation, the code, maybe there's mistakes in there, but once you get it ironed out, I mean, it's solid. There's no arguing, you know? And then you could leave it up to the computer to do sort of maybe machine learning in order to figure out new theorems. So you're doing kind of a numerical type optimization in order to find theorems, and you know, the sky's the limit. It's just, it blows my mind. Okay, I'll see you next time.